Hello everyone, this is Ashutosh Tripathi, fourth year student, BSMS student at Ising. Um, I will be presenting the topic quantum Ising model. Now let's start. So quantum Ising model is a quantum variant of classical model. From classical picture, we know that this Ising model it features lattice by considering only nearest neighbor interactions determined by alignment or anti-alignment of spin projections along the z-axis. Not only nearest neighbor interactions, the alignment is also governed by the external applied magnetic field. If we don't apply any magnetic field, then the only term in the Hamiltonian is this nearest neighbor interactions. Now the question is why we need this quantum picture, why classical picture is not sufficient to explain the behavior of all kinds of lattices with all kinds of possible particles at the lattice sites. So when we consider fermions and any quantum particle at lattice sites, then the spin projection along the different directions are no longer commuting observable. As we know that when we go from classical picture to quantum picture, the variables like position and operator variables they become commutators. So similarly here also in classical picture we had this spin variables. Now we have spin operators, and spin operators are subject to constraints given by their commutation relations. So the problem is that now the spin projection, the spin operators, they are no longer commuting observables. We cannot measure them simultaneously. Now, therefore, the classical statistical theory couldn't explain the model, and quantum treatment is needed. Now, let's see the Hamiltonian of the model. The Hamiltonian of the quantum Ising model has a similar structure like the classical has. This is the interaction term, and this is the external applied magnetic field term. The indices I and j are representing lattice sites, and the sum is taken over all the pairs of nearest neighbors. The prefactor j has dimension of energy, and factor g indicates the strength of external applied field relative to nearest neighbor interactions. The xj and zj represent components of spin algebra acting over spin variables of corresponding sites. So these two factors or these two terms act simultaneously, and the net response of the system is the balance effect of these two terms. Now, a very important concept that we need to discuss, that we should discuss about the 1D quantum model is the kind of phases that it possesses. So in 1D model, each lattice set is a two-dimensional complex Hilbert space. The Hamiltonian of 1D quantum model possesses Z2 symmetry. What is Z2 symmetry? It remains invariant under the transformation of flipping of all the spins about Z-axis. So as we know that every phase transition involves some kind of a spontaneous symmetry breaking, the 1D model also has two phases depending on whether the ground state preserves or breaks the spin flip symmetry. Uh, how we can solve this model exactly for all the coupling constants. Later on, the various scientists solve analytically this model. They gave the complete spectra of the Hamiltonian of this 1D quantum model. We will not go into the details of that, but we will shortly see the transfer matrix formalism for this model. However, the solution becomes too inconvenient to write down in terms of spin variables explicitly. So let's first discuss the kinds of phases. So when mod j is less than 1, ground state breaks the spin flip symmetry and the system has twofold degeneracy. This phase is known as ordered phase. Now, after assigning this kind of phase, now let's see the effect of j. So for j greater than 0, uh, in this ordered phase, for j greater than 0, the ordering is ferromagnetic, and for j less than 0, the ordering is anti-ferromagnetic in nature. Here, this is one example of this kind of phase. For g, we have this limit on mod g less than 1. So for let's take the value of g to be 0. For g equal to 0, we have these two kinds of interactions, these two kinds of orientations possible for the spin particles that are present at the lattice sites. One is the ferromagnetic. These two both are ferromagnetic in orientations. In ferromagnetic orientations, the orientation of all the spin particles are in the same direction. And antiferromagnetic orientation is also possible for G less than zero. In antiferromagnetic orientation, the adjacent spins they align anti to each other. Now, when mod J greater than 1, the ground state preserves the spin flip symmetry and is non-degenerate. The system in this situation is in a disordered phase. As an example, when G is infinity, the ground state has this configuration where all the spins pointing along z direction at each lattice side. And we discussed in classical picture that when we change the temperature, there is this critical temperature at which the system changes its phase. It goes from disordered phase to ordered phase. That is called the ferromagnetic paramagnetic transition. Hope you guys remember that. Now, one more additional kind of phase that is important to discuss is when mod J equal to 1. So what happens in this condition? The system has gapless excitations. The system undergoes a quantum phase transition. These excitations and the behavior of ground state in this phase are described by Ising conformal theory, which we will not be discussing here. Now, very important concept is the classical quantum correspondence. What is this? Let's discuss. So, we can map the classical d-dimensional Ising model to the d-1 dimensional quantum model. We don't have to do anything extra for writing the solutions of the quantum model. Every time for writing the solutions of quantum model, we can import the solutions of the d+1 dimensional classical solutions. Let's see how. So firstly, we will look at the transverse matrix formalism. Say, transverse matrix formalism is a method which is used to solve for the solutions of the Hamiltonian of the Ising model. And let's see what this formalism is. So firstly, let's see the formalism for the 1D model. Then we will extend this to 2D, and then we will try to construct the quantum formalism analogous to 2D classical model. So this is the partition function for the 1D classical picture. Now we do these substitution. We choose these basis vectors. We introduce these matrices. I will not go into the details of these calculations. You can see these calculations in the reference that I have attached in the last slide. So the Hamiltonian of Ising model can be rewritten in the form of these two matrices V1 and V2 that we defined here. Now, this is the new Hamiltonian, and now when we find this Hamiltonian in terms of the V matrix, which is nothing but the product of these V1 and V2 matrices. Now, now let's extend this formalism for 2D model. Now, what in 2D model we have this n into m dimensional lattice. Now, in this case, we will have 2 raised to m configurations, 4 raised to power m configuration of the rows. So it's very easy to extend the 1D model to 2D model. Now the structure of these matrices V1 and V2 will be like this. And now the partition function for the 2D system can be written as this, where V1 and V2 have similar structure, it just have two-dimensional interpretation. Similarly, the transfer matrix for the two-dimensional model, which acts on a 2m dimensional Hilbert space, which can be viewed as an imaginary time evolution operator connecting neighboring rows, where the neighboring rows are nothing but the quantum Ising chain. If we see the Hamiltonian of 1D quantum Ising model, which is this, we can see that the structure of the 1D quantum Ising model and the structure of the 2D Ising model is same. And by this, we can we can see the correspondence, clear correspondence between these two models. And not only this correspondence, there's also shows the correspondence between Boltzmann term and the time evolution operator. In classical picture, we had this Boltzmann term, and now we in quantum picture we have this evolutionary time evolution operator. So this is a very interesting topic. Now, if we talk about the exact spectrum of the 20 quantum model, so they were in 1961, Liu, Schuld, and Mattis derived the exact solution of couple of quantum 1D models through finding the basis in which Hamiltonian becomes diagonal. So this is a very important thing, that we have to find a basis in which Hamiltonian should be diagonal, then it becomes easy to solve the problem. So as we know that in quantum quantum model, the spin raising and lowering operator satisfy these commutation relations. And before diagonalizing the Hamiltonian, we require an additional step, because these commutators, they are not invariant under linear transformations. So we cannot go into a basis simply by performing some linear transformation. We have to do some additional things beforehand. For resolving this issue, we have two well-known methods, that are Jordan-Wigner transformation and this Bogoliub transformation. I have discussed these two transformations in detail in the term report, whose reference I have attached at the end of this presentation. Please go through that if you are interested. And through these procedures, these two transformations, we can map the spin system to a system of free spinless fermions, providing significant analytic insight into the behavior of the ground state as well as excitations. Now, let me summarize my discussion, my presentation. So, in this presentation, what we did is we started our discussion with the quantum Ising model and the structure of its Hamiltonian. Then we looked at the kinds of phases that 1D transverse field model. This quantum Ising model is also known as transverse field model. So, this is nothing new. It's just a new name for the quantum model. At last, we saw well-known mapping between the 2D classical model and a 1D quantum model. It is a special case of a D-dimensional to D-1 dimensional classical D quantum correspondence. Thank you, and that's it.